Hi students, our today's video is on Lewis dot cross structures. We have done quite a lot number of examples by now. In today's lecture we'll see some more example. Let us begin. We want to make CH4 CCl4 SiCl4. We need atomic number of carbon 6 and electronic configuration of carbon 2 4. Same thing we need for CCl4 as well. We will also need chlorine, atomic number 17. We'll also need its electronic configuration, which is 287. Then we need silicon, atomic number is 14. Carbon, silicon both belong to same family, carbon family. Carbon, silicon, germanium, tin, lead. So electronic configuration 284. They belong to same family and hence they have same number of electrons, that is 4, in their valence shell. You can see. This is something very simple. So I want to make methane. So carbon with 4 electrons and 4 hydrogen. Very easy. Very simple. And that is how it makes the tetrahedral structure. This is the contribution of hydrogen, 1 electron of hydrogen. That's how it is making 4 bonds. And the geometry of the molecule is tetrahedral. So this is tetrahedral structure. Okay. Let us see CCl4, exactly same, something very simple. Cl4, carbon will have 4 electrons, so it is contributing its 4 electrons of the valence shell. Each chlorine has 7 electrons in the valence shell, of which 1 it is contributing to make the bond, and remaining 3 electron pairs, that is remaining 6 electrons, form the 3 lone pairs. This is the first bond formed. Then again same thing here. 7 electrons in the valence shell of carbon, of which 1 participated in bonding with carbon. Same thing here, 7 electrons in the valence shell of chlorine, out of which 1 participated in making the bond with carbon, you can see, and the remaining 6 electrons are the 3 lone pairs. Same thing here. And 1, 2, 3, 4, 5, 6, 7. So these are the 3 lone pairs. So that is carbon tetrachloride. Again, it is also a tetrahedral structure. This is also tetrahedral structure. Then we have SiCl4, exactly same, no difference at all. Silicon is having 4 electrons in the valence shell, just like carbon, and 4 chlorine at the 4 corners of a tetrahedron, contributing 1 electron for the bond formation. This is 1 bond formed, another, the remaining 6 electrons are left unused. They are the 3 lone pairs. 1 electron used and 6 left in the form of 3 lone pairs. Same with this, chlorine contributes 1 for the bonding and there are 3 lone pairs unused. This is also tetrahedral structure. So that is how we can understand the structure of methane, carbon tetrachloride and silicon tetrachloride. All are tetrahedral structures. You can take a look at it for around 10 seconds. Then I will erase it and we move to the other structures. Okay, I'll just erase this. We go to the next set of examples. And the next set of example is really mind-blowing and interesting. And that is, I'm taking, really interesting, just see what I'm taking. Taking NH3, okay. And I'll make NH4 plus. Really interesting. And I'm doing pH3. I will be making pH4 plus. Let us see how the changes take place. I'm just entering the names. This is ammonia, everybody knows. This is ammonium. This is phosphine. And that's phosphonium. Phosphonium, right? Let us see the structures. The central atom is nitrogen here. Central atom is nitrogen in this case also. Central atom is phosphorus and here also the central atom is phosphorus. Now they have 5 electrons in the valence shell. Each one of them obviously, because nitrogen is nitrogen, nitrogen is nitrogen, 5, 5. Phosphorus belongs to same family. Nitrogen, phosphorus, arsenic, antimony, bismuth. So it has 5 in the valence shell. And this phosphorus is also having 5 in the valence shell. So this is how we have made the central atoms. Now 3 hydrogen. So obviously 1 bond here with H, another bond here, other H, and a bond here with other H, and this is the unused bond. This is unused, it's bubbling with energy. This is the unused electron pair, that is the unused, that is called the lone pair. So these are the unused electrons which are nothing but the lone pair. Let us see here. 1 hydrogen, it is making bond over here. Another hydrogen, it is making the bond over here. Okay. Then yet another hydrogen, and this is the bond formed. Now this lone pair is not unused now, because you see there are 4 hydrogen, of which one of the hydrogen is a proton. I hope you know what is proton. I'm just writing that. Proton is H plus, meaning it has 0 electron. And we know hydrogen makes a duplet. So proton needs 2 electrons. So this proton comes H plus, and this nitrogen will give will contribute both the electrons of the bond, and then the sharing of electron will take place, and this is how ammonium is formed. The plus charge is dislocating on the copodia. So that's ammonium. That is ammonium. Now the difference between this and this is a lone pair, this is a lone pair, but this is unused, and here it is used to make the, do you remember the name? To make the coordinate, I hope you remember, to make the coordinate covalent bond. Whereas these three are the covalent bonds, whereas that is the coordinate covalent bond. Now this structure is tetrahedral. You can see it's just like four corners of a regular tetrahedron. So the structure is tetrahedral. Okay. But in this case, this is a lone pair. It is unused electron pair, and hence it is full of energy. It experiences more repulsion than the bonded pair. So because of repulsion, this orbital is far ahead, and the structure looks something like this. It is not having this bond length because these electrons are used. This is unused, so lot of energy. It's repelling. Lone pair and bond pair repulsion is very high. As a result, this structure appears like a pyramid. So although ammonium is tetrahedral, but ammonia is pyramidal. What we should know is repulsion between lone pair and bond pair is more than bond pair and bond pair. Let us see this. Exactly same. This one bond formed, the second bond formed, and here the third bond is formed. And same way, this is the lone pair, so full of energy. So this is also pyramidal. So phosphine is pyramidal. But in this case, just like ammonium, one bond formed, another bond formed here. Yet I'll just move it little bit that side, children, so it will give you a better view. Okay, this is the other hydrogen, and this is also used with the proton. So this structure will be on the copodia a plus. So this is tetrahedral. So we have seen how ammonia and phosphine are pyramidal because they have an unused electron pair, that is the lone pair, which repels and makes the structure distorted tetrahedral. बिगड़ गया, खराब मतलब चेंज हो गया स्ट्रक्चर, और वो डिस्टॉर्शन, वो गड़बड़ क्या है, पिरामिड बन गया, पिरामिड. But ammonium is tetrahedral. Same way phosphine is pyramidal, but phosphonium is tetrahedral. That's all for today in this video. We're meeting next time. Till then, bye-bye. Take care. Love and blessing.